Yes. But also, like, it's the most fun you never want to have again kind of thing. It's like, I can't wait for this fun to be over.
No, you're gonna be great. I saw your Instagram post. I opened up my phone last night and I saw your school ID photo and I'm like, look at this guy.
So today, all I had planned, I was going to make sure that you guys had all seen that I'd posted the review. The review and the test will be similarly formatted, so same kinds of questions, approximately the same quantity of questions. So you have like an integration by parts problem, a partial fraction decomposition problem, just verifying that this is a solution to this differential equation. How do you do that again? You just take the derivative and then plug it in and show that it like simplifies down. Like that's all you need to do. Not a big deal, right? Sketch a solution to a slope field. That's like a 30-second problem there, right? Use the slope field to determine the equilibrium solutions. What are you looking for? Yeah, x's or y's where the slope field's horizontal. So what do we see? Like 1, 2, 3 x's, and then looks like 1, 2 y's to me. So again, like a 30-second problem, you just got to be careful that you catch them all. But there's nothing to do. You're just using your eyes, right? Solve the differential equation with the initial condition given. Here I say you do not need to write your answer with y by itself. You'll find that it's actually going to be unreasonable to try to do that, even if you wanted to. Solve a differential equation without initial condition. Here you should get the y by itself. It should be pretty easy to do that. Here's a linear differential equation I ask you to solve. Here's a differential equation with an initial condition. I ask you to use Euler's method to approximate the value for y2. I then ask you to solve the differential equation with the initial condition and then use that answer to find the exact value for y2 and compare your approximation with the exact value. And then our last question is again, you're given a differential equation it has a story problem setting. And then we ask you some questions about this. So like, which one is, the thing happening faster with whatever the context it is. Here you're asked to find the second derivative and then explain why the graph that's given cannot be a graph of the solution. Hi. No problem. So how would we use what is the second derivative going to tell us? How can we use that? Very good. Mackenzie says it tells you the concavity, whether the graph is concave up or down. Do you remember which one is which, or how do you tell from the second derivative the concavity? Great. Positive and negative is going to tell you whether the graph is concave up or concave down. Do you remember which one is which? Concave up is positive, concave down is negative. So if I look at this graph here, I notice that we have a concave up section, like right here, and a concave down section right there. So I'm suspecting when I take the second derivative that I'd find that second derivative is going to be always either positive or negative, which would mean that this could be impossible since it has to have both. Since it's concave up in places and concave down in places, its second derivative would have to be negative someplace but positive some other place. And if the second derivative we actually find is not that, then we know this couldn't possibly be a solution. And then just a good old use separation of variables to solve the thing with the initial condition. What do you guys think? Sounds like chapter 9, right? Not a lot of surprises, I hope. Do you want to just open up for some questions here now that we had a chance to kind of talk through what's going to be on there? Kenzie? On the review?
Yes.
Sure, we can do that. All right, Mackenzie, what's up with 9C? Just the difference between your approximation from part A and evaluating y of 2 with your answer for part B. So in part A, you found y of 2 is approximately something. In part B, you find an equation for y of x. You just use that to get the exact value for y of 2, and then you look at the difference between the two, the approximation and the actual. Does that feel okay? Mia. Yeah. Mm-hmm. So you only, when you do something to both sides, you know, like if you have that is not equal to doing that. That you cannot do. You can do this and then separate using our rule for multiplying exponents. But exponent base to both sides is not distributive. It is strictly to the whole side, and then you can separate using your exponent rules, but you can't just like term by term handle it. Does that feel okay? Yeah, no problem. Blake.
Why do you have a minus plus sign in your answer? Like, I understand algebraically why that happens, but like, doesn't that not matter because isn't a minus plus contingent on what? Yeah.
Well, we already found C, right? Okay. We're solving for a value for B.
Okay. Oh, and then, yep, okay, I see.
And clearly in that sense, B could be, you know, like I have to worry about the negative and positive here because with plus or minus, both of those could give me a positive value for B since it's the weight of a bird. And both of those would be feasible.
Okay.
Right?
Yeah.
You know, if T is 0, you know, 120 plus 95 and 120 minus 95 are both feasible bird weights. Right?
Okay, I see.
So that's why I got the plus or minus. Still rattling around in there. Does that feel okay? Because this question actually asks you to do a couple of things, right? So it wants you to, you know, like solve for C, right? And then once I have figured out C, I had to go back to this piece and get the B separate by itself. So that's what we did there. Is that okay? Mackenzie? All of 8 from the review? Sure. Where did that go? This guy. Okay. So the first thing we would need to do is to get us into this form, right? So the dr dt is my y prime. So the first thing I'm going to do is divide both sides by t over the natural log of t. And I notice that stuff is going to cancel. So far, so good? Okay. So the r is like my y. So this is like my y prime plus my p of x times my y equals my q of x. Is that so far so good?
Yeah.
That's okay. What I'm going to now do, now that I have it in that form, is calculate my integrating factor. So to do that, I take the integral, I'm sorry, not the integral, I do e to the integral of p of x dx, or in our case, that's going to be e to the integral of 1 over t times the natural log of t dt. That's going to require a u substitution to do. So the u I'm going to pick is the natural log of t. So du is 1 over t dt. So when I make my substitution, that just becomes 1 over u du. So we do the antiderivative for that. So that's e to the absolute value of u, or just the absolute value of u, or just the natural log of t. That's not what I meant to open. That's what I want to open. And I dropped that absolute value. Why did I drop that? Just think for one quick second. Okay, so here's my justification why I'm going to drop the absolute value. What am I going to do with the integrating factor? I'm going to multiply it to both sides of the equation, right? So if it's positive or if it's negative, either way, if I'm doing it to both sides, if I multiply both sides by negative, that's like doing nothing at all, right? If I multiply both sides by a positive, you know what I'm saying? So like I can drop the absolute value here because of what I'm using this to do. Is that okay?
Yeah.
I had to think about it for a minute why I did that. So that's what I need. Well, here's what's going to be, here's why you're going to have an issue if you keep it. So let me just show you for a second. So now I will rewrite this. So the left-hand side is becoming the natural log of t. That's my I of x. Well, let's write it this way. So we can write that then. Is that okay? So here we would have natural log of t times r equals to my q of x, which was e to the t over natural log t, and my I of x is natural log t. So if I keep the absolute value, Mackenzie, I wouldn't be able to do that reducing. And that's going to make life considerably easier. That's why I was, why I know I needed to drop it. Because if I didn't, like, what am I going to do with that? So we'll integrate both sides at that point. I guess I should put a dt over here if I'm doing that. I don't need it over here because I have the prime on it. So I know that the integral just cancels out the derivative. That's just the fundamental rule of calculus. E to the t dt, the antiderivative of that is just e to the t. And I'll put my plus c on there. And again, what I'm doing is trying to get the y by itself. So I'll just divide both sides by the natural log of t. Since the r was like my dependent variable there. And we're all done. Okay, so yeah, so what we're really writing here, let me write it a different way. this is really what we have there. Oops, I don't write the dt. Okay, now the fundamental rule of calculus says that an integral and a derivative are inverse operations of each other. They just cancel each other out. So the integral and the derivative cancel each other out. So you're left with just the integrand there, the natural log t times r. Is that okay? Which makes sense, right? What do we use to go backwards from a derivative? We use an integral, you know? Does that feel good? You're happy? Good. Blake, stretch your hand.
I'm stretching.
Okay. John.
23.
9.6. 9.2. Yes. Okay. Use Euler's method with step size 0.1 to estimate y of 0.5, where y of x is the solution to the initial value problem. Y prime equals f of x, or y prime equals y plus xy, where my initial condition is y of 0 is equal to 1. So to do this, I'm going to be using my Euler's method formula that we talked about in this section. So if I am starting here, where x0 is equal to 0 and y0 is equal to 1, and I'm going to y of 0.5 by 0.1s, I'm going to have to do 5 steps in my Euler's method, right? I'll need y1 will give me when x is 0.1, y2 will give me x is 0.2, et cetera, et cetera, et cetera.
Wait, but how do we know x down is 0?
Well, because the initial condition is x is 0, y is 1.
Right.
So we have h, we have y, 0 and x0. So if I plug in my formula, we're doing that, right? y1, or y0 is 1, h is 0.1, and f is the derivative. So when I do that, I'm going to be plugging 1 in for y, 0 in for x, into the derivative given up here. So that's going to give me 1.1.
Okay, and then that's your, you put that where the 1 is.
Right. So now I have the point is my first approximation is this point.
Okay.
So y2 is going to be then y1 plus h times f of x1 y1. So my y1 is now 1.1. My h still stays the same. I have y plus x times y, and then calculator time, and I just kind of repeat that until the end. Does that feel okay? Yes. Yeah, because this will give me then 0.2 something. You do y5, and that'll give you our approximation when x is 0.5. Does that make sense on how we did that? So again, you definitely would want to remember that Euler's method formula that we just looked at. Since there's a question asking you to do that on the test, you'll definitely want to have that remembered. But fortunately, it's a pretty easy one to remember. It's basically just like the slope equation or the slope-intercept equation, right? And just like this is like y equals y1 plus m times x minus x1, right? It's basically just that. It just like generalized. That's how I remember it anyways. Who's next? And John, I'm not going to finish this because at this point, like you see what to do, right? Like it's just going to be like 10 minutes of watching Mr. Kulik write down numbers and grind them into his calculator, which is fine. I'm happy to do it, but like we don't need to do it. Mackenzie.
Number
7 from the review. Yes, sure. And I picked that. Oh, there it goes. All right. So we're asked to solve the differential equation. So we want a y equals equation basically out of this, right? I noticed right away that this is separable, right? That there's not a whole lot of... Oh, I see why you're confused. Because the key makes no sense, huh? I think I just typed that down wrong. Yeah. No, it's, I mean, do you want to solve it for what I have written down or what I meant to write down? Okay. So we're just going to do that and put the y in the numerator instead of the denominator. Oops-a-daisy.
It's still possible to solve that original state.
Yeah, you'll just have like a square root or whatever.
Oh, okay.
But it wouldn't be massively different. So when I separate, I'd have 1 over y dy equals natural log of x over x dx. And if you did it the other way, you'd have y dy equals natural log of x over x dx. So we'll do them both alongside each other since at that point we'd be ready to integrate. The antiderivative of 1 over y is the natural log of y. To integrate natural log x over x, I'm going to need to use u substitution. So the u there you'd pick would be the natural log. So du is going to be 1 over x dx. So that just turns into u squared over 2 plus c. And when I plug that u back in, that's the natural log of x squared over 2 plus c. Does that feel okay, Mackenzie? Okay. So to next order of business would be to get rid of the natural log there to get the y by itself. So we'll do exponent base e to both sides. And I would now separate that exponent we can call e to the c, well, let's do that. We'll do the plus or minus first. And then you could take the whole plus or minus and suck it into, and just call it c if you want to. You could leave the plus or minus out front also. It's not wrong to do that. Or you can just suck it up into the constant. That's okay also. Just vacuums up in there. Now if we had done it the other way, the only difference is that the right-hand side, I'm going to get y squared. Over 2. So I'd multiply both sides by 2. But 2c is just c. And then we'll square root both sides. And you write that. So whether you did the question I meant to do or the question that was written down, there's the answer for both of them. Sure, no problem. The question I wrote down might have actually been a little bit easier, right? Because you have all the natural log stuff to mess around with. Sorry about that, Mackenzie. Definitely understandable to be confused looking at the problem and looking at my answer. You know, you go and proofread something and you still make a kulik. So, I get it, guys. I get it. Anybody else? Blake?
This is very general.
Sure.
Could you explain, like, in words, like what Euler's method does differently than what all the other methods of this?
So Euler's method is just a way to approximate solving a differential equation.
Okay.
So like basically what you're doing is you have like, let's say that this is the actual solution and this is some point on it. What you're doing with Euler's method is you're basically like pretending that you're a line. So you're like building like a line, a linear approximation from some little piece of it, and you're piecing that all together. So like that green stuff would be like the Euler's method piece. And you're just getting it like, you know, you'd have some then error associated with the approximation.
Okay.
Where there's some difference between the actual value and the approximate value. Now, if you pick that step size to be small enough, infinitely small in fact, you will get the correct answer, but like practical terms, why do we bother with this? It's because sometimes solving one of these differential equations is like actually kind of impossible.
Okay.
Like the integral you're being asked to do is maybe not even feasible. So what are you going to do? You do an approximation. You just have to be fine enough with your approximation to make sure that it's still good. But that's all you're basically doing with Euler's method, is you're just like pretending this is just a bunch of line segments connected together. And if you make those line segments short enough, you get a pretty accurate representation of a smooth curve.
Okay.
Does that
Yeah,
make
that
more
makes
sense
Yeah.
as to what it is that you're doing?
Yeah.
And again, the big picture really helps understand what you're doing, right? Like if you think about it that way, it's like, okay, so that's why we're just like the end point for the first approximation becomes the start for the next approximation, because the two segments need to hook up together. And you're just taking the slope at that start point and using that, to make your line, and then stops, and then the slope at that point where you stop becomes the new slope for the next segment, and you just kind of keep stepping through. Not at all. To the one that I gave you? Yeah. It's not going to be like, oh, look at this. It's like, no. I mean, I tried to make it something where it wasn't going to, like, there's 10 questions on here. That's not, like you have unlimited time here. I tried not to make something that's like, oh, this is just going to turn into like this one problem. It's going to be 10 minutes, even if you really know what you're doing, just because there's that much like algebra you have to really be careful with kind of stepping your way through it, and there's going to be nothing bonkers where I have like like a quadratic piece in there, like a quadratic factor that's not factorable, where you have to do like instead of a over whatever, it's like ax plus b over whatever, or nothing with like terms with multiple degrees in them. Like I won't have like, oh, this factors down to x plus 2 cubed times x minus 7 or something, and when it's like, oh, now I need like 4 of these fractions. Like this is just basic. You'd understand the process in the most basic sense. You know what I mean? I mean, it's still AP Calc, so it's still like pretty complicated, but that method is a BC method. It's just something I remember doing in, Calc 1, 2 that I feel like we should do. And there's a couple of other things like that still that I would like to take a minute to do. The BC methods that I've chosen to do is either because I would have to be super careful about the homework problems I was choosing, because these methods kind of pop up in things that I would have wanted to do. Is why we did some of these before we got to the review stage. But I'm still going to sprinkle in a couple more topics here into the review stage that I think are good things that you would typically see in a Calc 1 or 2.
The sensor does not link.
Yeah, you got it. Yeah.
Anybody else? Questions or whatever? Oh, man. Okay. Well, that feels good for me.